Welcome everybody to another edition of the CBAR webinar series. I'm Andreas Park. I'm a professor at the University of Toronto, and I welcome you all to this session. I'm very happy to have Davide Crapis. Oh, I got your name right. I'm so sorry. I should have paid more attention earlier.
Oh, this is good.
So he is from the Ethereum Foundation. He works in the robust incentives groups. He has done very interesting and important work on fee mechanisms in Ethereum. And he will talk today to us about EIP 4844, which is Ethereum scaling solution and danksharding. And so I'm very much looking forward to hearing a lot about how Ethereum will be made faster and sleeker and can do more things than it can do even now. So Davide, I will soon hand over to you for all the participants. Just as a very quick note, the way we will operate is there's a Q&A session where you can post question and answers, questions really that I will see. If I feel that they deserve immediate attention, I will directly put them to Davide. Otherwise, we're going to have certain breakpoints in the presentation, at which point I will ask these questions, and I may call upon you also directly asking you to ask the question directly. So with that, Davide, I'm going to hand it over to you. Thank you so much for agreeing to talk to us, and the floor is yours.
Thanks, Andreas. I'm going to share my screen. Yeah, thanks for the nice introduction. So basically, I'll talk about what's ahead for Ethereum scaling, starting from describing the current solution for 4844. We just went live about a month and a half ago on May 13th. And then I'll try to also talk about potential solutions that we'll need on the horizon. So I'll start by giving kind of high-level introduction to the Ethereum roadmap and the role of roll-ups in the Ethereum roadmap, right? This is fairly recent, but it's kind of an important milestone which determines the structure of the market today on top of Ethereum. Then I'll describe the EIP 4844 market design. This is made of two parts. There is a new transaction types, which roll-ups, but anyone, of course, can permissionally use to send data to Ethereum, layer one. And then there is also a fee market to price this new type of resource that gets introduced. So I describe the design. And then I start focusing on what's beyond EIP 4844. So the first part will be based on some research that we have already done. This is based on two papers that we published earlier this year with two sets of co-authors, which relate to the current structure and what we need to do going forward. And then in conclusion, basically, I'll give a more kind of data-oriented overview of what's happening in the market now in this month and a half that this new market has been live. And I'll point to, as you were saying before, some direction to improvement, what we can do to make Ethereum even better. And since the audience, there's many researchers in the audience, also questions that are still open, we are tackling today. Okay, so roll-up centric roadmap. Just very high level, the mental model for Ethereum is it's this computer in the sky, right? It's not a cloud, it's really in the sky. So you think about it as a global distributed computer, essentially it runs programs that are deployed, committed by anyone. And the key feature of this computer in the sky is that essentially there is a large number of nodes that run the same programs and come to consensus on the state of this machine. But there is a problem. Computers have a finite capacity, and so there is scarcity of resources for people that want to execute programs on this computer. And this is a problem because it increases fees and it lowers user welfare. So maybe before I go into this, let me also add that this is a key problem in blockchain design, right? Like up until a few years ago, people that have been in the space for like a couple of years have heard about the blockchain trilemma, right? That you cannot have like decentralization, security, and scalability at the same time, right? And this scarcity concept is one of the key reasons. So initially, Ethereum was trying to do a solution called sharding. So basically, the state of the Ethereum virtual machine gets sharded into like 64 partitions, basically, and then get partitions into 64 shards, and then essentially these shards execute in parallel. The problem with execution sharding is that it's limited. Like you cannot really scale above 64 shards, and it's very rigid. So the new idea came about of essentially executing programs off-chain outside of Ethereum, and then reporting computation back to Ethereum, which is the trusted computer. And essentially, the core concept in rollup scaling is that Ethereum needs to be convinced that the program was run honestly without having to rerun the program, right? Because otherwise there is no scaling. You still need to rerun the entire computation. And basically, this is a direction that was coming to consensus around 4 or 5 years ago. And since then, we have seen an explosion of rollups on Ethereum of different kinds, which I'll briefly go into it. But before it, just to understand what it means to compute off-chain and then report on-chain, I want to give a small example. So essentially, this is a small example of a token transfer, right? When you transfer a token, you need to run a computation that updates the balance on the sender account and the receiver account, right? So you can do it off Ethereum. So for example, the way you would do it is I transfer my token off-chain, perhaps from Ethereum mainnet to Arbitrum. And then let's say that I am Bob. I deposit 3 tokens on Arbitrum. I send 1 token to Alice on Arbitrum. And then I want to withdraw my balance back to Ethereum. And essentially, the idea here is that Ethereum needs to know how much to give me back. And it needs to do so without having to rerun the transaction for the token transfer, right? So there is 2 ways that in rollups design you can do this. One is optimistic rollups, right? So essentially, this is a solution that is based on crypto economics. So you assume that the result is correct until someone else proves that it is not. And in order for this interactive fraud proof, this game theoretic mechanism to work, you need 2 things. You need all the data to prove that the transaction was incorrect in the case of a challenge. And then you need enough time for people to being able to essentially pose the challenge, right? Usually this is 1 week. And this is what optimistic rollups use. The other concept, which is based on cryptography, is validity rollups, right? So essentially, the validity rollup is a construct where each computation is comes with an associated cryptographic proof of validity. So the rollup is audited in advance. So you know that like whenever you have a validity proof, the computation was run correctly. So basically, you just need to post the state or the resulting state of the chain, and the proof that that resulting state was obtained via a correct computation. So like as we've described, like now like both types of proofs require data to be published to Ethereum. In the good case, Ethereum doesn't run any computation, but data needs to be made available. The interesting thing is that this data does not need to stay on Ethereum. For example, in the case of optimistic rollup, does not need to stay beyond the period of a week, the challenge period, because after that, like the transaction is settled, no one is challenged. You just need to like publish data on Ethereum for common knowledge, basically. So this brings up a new resource, right? Now, like we need data, potentially a lot of data, which can expire, like which comes with an expiration date. And so enter EIP 4844. So actually, let me say that rollups were already posting data to Ethereum before 4844, right? Like Arbitrum and Optimism have been around and at scale for a while, and many others were also present before March 13th. So what they were doing is basically they were using normal transaction, regular transactions, and there is a field in the Ethereum transaction for data. So they were just like packing as much data as they can in the cold data field of the regular transaction. And so now 4844 is also called proto-dunk sharding, as Andreas was introducing. Proto because there is a full dunk sharding coming down the line. It's like the first solution which introduces actually this new resource, right? This data that expires, which is going to be cheaper. And so like in order to do this, basically we need two ingredients. So one, this new transaction format, which carry a data blob. And it already has all the cryptographic properties that we need to scale to data availability sampling, which is the full dunk sharding solution. And then we need to price this new transaction. So we also need a new fee market for these. And maybe let me add that this is a solution that is designed for rollups, which are like heavy users of Ethereum data, but anyone can use them, right? This is like the beauty and also challenges of like an open permissionless economy. So I'll comment on this again when I show you the data of like what happened in the past month. Cool. So basically, one thing that I want to start mentioning, because in the next section of my talk is going to be important, is that now this creates a dual market for transactions, basically. So there is like standard transactions that are priced using only the gas EIP 1559 style metering. And then there is blob transactions, which blob transactions still require to use some gas, because like there is some compute operation that you need in order to make sure that this data is posted in the correct way, right? That is registered by the correct rollup smart contracts, etc. So blob transactions are actually subject to like kind of this dual market where like they pay a little bit of fee for compute, and then they pay like a fee from data. And this chart is just depicting that like resource one, in this case, standard transaction, they only depend on price of resource one, which is gas, while resource two, which is blob transactions, they actually like are influenced by both gas price and data price. Okay, so what's beyond 4844? So the first kind of deep dive is based on like recent work I did with some colleagues at Columbia Business School, Shou Zhao, Wang, and Siamak Moallemi. So this looks at post 4844 from the perspective of the layer 1. And then we'll also look from the perspective of the layer 2. But essentially, like, maybe let me say, this work essentially looks at, now we have this dual market, right? Then what happens? Like, it's the first step towards like unbundling, opening up the fee market to like many more resources being priced. And essentially in this work, we are asking the question, like from a system control perspective, is like, what is the optimal way of dynamically pricing like multiple potentially arbitrary number of resources in Ethereum? So EIP 4844 I already introduced. Here, let me say a little bit more about what are these new resources, right? So essentially, like with 4844, we created a resource which is derived from data, right? Like you can think that Ethereum is like a virtual computer as basically like 4 or 5 principal resources, which is like compute, network bandwidth, memory, state access, and data. And essentially what we did is we took data and we created a new resource which like also has this expiration date after 2 weeks. And this is a new resource that now the protocol is selling, right? Similarly, we can do with other type of resources, right? Essentially the question here is demand comes in bundles of resources, right? As we've seen, like the blob is a bundle that consumes both compute and data, and of course like bandwidth, etc. So like how do you price these bundles? This is the question we are after. So I'll give maybe like a high-level introduction to this. It's not going to be like super deep into the technicalities of the paper. I'll present kind of the main result for the interested audience, but I suggest also to like check the paper. Is like it was published in the Financial Cryptography Conference, so it's a short paper, but I think people that are working in this space will find it nice. But basically, like what we do is like we set up a framework. It's really like it doesn't say anything. It's agnostic to the type of resources you want to define, right? It just sets up like a vector of resources that you want to price. And the reason like we set up this framework is because like this is kind of early stages in like multi-resource pricing research. So we want to like explore like a generic way of doing things, which is also simple. So like simplicity is also like a design goal for us, because the idea is that like a mechanism like this could be implemented on a layer 1 or a layer 2. And then we look at robustness properties. For example, we cannot condition the pricing based on the mempool demand, because that's not Sybil resistant, right? We can only check the gas that was consumed, so the realized demand, which cannot be spam attacked. And then we look at optimality from like kind of optimization perspective.
So can I ask you, just out of curiosity, I mean, so one application that jumps to mind right away is we have a large number of tokens and also smart contracts that are on the blockchain as it is, but they're never used. I mean, you know, like there are professors that create tokens for their classes that are somewhere in the data and never used after, right? So it would be useful to have a system which would either have a price that is ongoing for this, or which would be one so that you have to keep paying in order for this contract to remain active, or you have some other form to to make sure that there is no abuse of space, right? Is that what you have in mind here, or is that something that you can handle, or is this beyond?
Yeah. So in this work, we don't look specifically at this, but it's an important question, right? And it's one that becomes even more important as like the protocol keeps on living and the economy on top of it grows, right? Like, I mean, the Ethereum protocol, like time scale, when I think about it, is like in the hundreds of years, right? It's not a company that like is born and dies after a decade or two. So these are very relevant. There is already efforts in this direction with like history expiry, pruning the state that is inactive. There is also experiment from other blockchains that are pricing like state differently based on like the congestion at the state level, not at the block level. But we don't go too deep into this, but I think those are all directions that will be explored in the future. Yeah, so good point. So maybe I was a bit too broad in the sense that in this work, like maybe my mental model is not going at the state level, still staying at the aggregate resource types, right? Like I just think that maybe like we define like 10 resources, which is like derived from like the core aggregate resources that the network consumes at the block level. But yeah, state level, maybe it's the next kind of, it's the next direction, which is seems exciting. What else is important here? Yeah, so essentially like the other thing is that we build a framework on top of like the 1559 mechanism, which is like a very I would say like simple but also powerful way of doing congestion pricing. So basically there is a target and a limit for the resource consumption that you can offer at each block, and you basically do targeting. And like our idea is like 1559 has a very simple static update policy. So the price changes, but it always goes up and down by 12.5%. It's like, can we find like a more optimal way of updating these prices? And then maybe the last part that I'll say as an introduction is that this framework can be used directly in the sense like you'll see that the optimal policy is actually like some linear combination of state variables that the protocol observes, so you can implement it. But then it can also be used indirectly. You can compare to what we're doing today with 1559 and 4844 and see like where the difference in performance is and things like that. Okay, so let me introduce. So like we have n resource and each resource has a target. So for example, in the case of 1559, the target is like 15 million gas unit per block. And for blob transaction is 3 blobs per block. And then at every block, the protocol observes 2 things. Observe the resource price, so like which was set by the protocol in the previous block. So in this case, the gas price and the blob price. And then it also observed the realized demand in the previous block. So how many data gas units were actually consumed and how many blobs were actually posted. And then basically we use like a linear demand function. So here on the right, I'm showing this equation for the demand function. So K, the index denotes the block here. So at block K, you have like the vector of Y, which is the resource demand consumed, which is basically like per resource intercept plus this like price response matrix multiplied by the prices of resources, right? And then there is some stochastic noise. So just to give an example, so here I'm doing the case of like two independent resources, right? So these are like two resources that can be priced completely in parallel. So like the demand system that I just presented, you can just represent it in these two charts. So where on the left we have resource 1, on the right we have resource 2, and then the beta are the coefficient in the matrix B. And so like here we only have diagonal terms because it's independent resources. The cross terms are both 0.
Can I just interrupt you for 1 second just to
Yep.
clarify? So you said first that there is 3 blobs per block. So the total would be what, 6? Or how does this work?
So the target for the protocol is 3 blobs per block, but you can post up to 6. So
Okay.
the 6 parameter is, or the 30 million parameter for gas units. That's like, we call it a burst limit. So the protocol like manages gas to be like our prices gas, right, to be at the target. But then fluctuations in demand are allowed up to the limit, basically. That's like a short-term control. If you want, like you, because like in steady state, or like how to say, like on average, even if you look at like 2 hours rolling averages, the protocol is going to consume like 15 million gas and less than 3 blobs. But in the short term, like you can consume more. Of course, if we were to allow like more than 30 million, then it's possible that there is other problems, like a block cannot be processed in time, and then the chain loses liveness. So it's really like kind of a worst case security parameter. Yeah.
Okay, and just to clarify again, the limit, so the total limit is in data size, you said, right? What do you say, 30 million?
Sorry, I think I may have confused here. So like for blobs, the total limit is 6, as you were pointing out. But there is a limit for gas as well, for compute, for the traditional gas, which is 30 million units. Yeah.
And just last thing, so so there's a limit for blobs, but the blobs also have limits, correct? So as in it's data,
the blobs
it's
also
data,
have
right?
capacity. Yeah. Each blob has like 125 kilobytes capacity.
Okay, so it's like 500.
Yeah. Like 375 target, and then 770 limit.
Okay, so I just, because I read somewhere else that the limit was supposed to be 1 megabyte of data that could be carried in a block. Did I get that wrong? Was on consensus blog or something.
Oh, it's almost 1 megabyte, right? Like it's like a little short than 1 megabyte. So maybe they just approximate to 750 to kilobytes to 1 megabyte. Yeah.
All right. Oh, okay. So just
We can think
okay.
it's in the ballpark of 1 megabyte. Yeah.
Okay, so just so clear, so a blob is roughly 150. Let's say, I mean, I'm approximating, right? So a blob is 150. You have 3 blobs, it's almost like 450.
Yeah.
Okay, and then total is about a megabyte. Okay,
Yeah,
got
exactly.
it. Okay, got it now.
Yeah. No, it's a good question. Maybe I should also point out that in this work, like we actually like both in this work and in the one I present later, we don't look too much into like the case with the constraint. We just look at the steady state and the target. And then we have like some details on how to set these constraints, but it's not our main focus, because at the end of the day, the target is what matters for like market clearing prices, etc. Yeah. Okay, yeah. So essentially, like, this is interesting, right? So now, like, I presented this demand structure, but the potential demand, like the intercepts, the Ds, and the price sensitivity parameters, like the Bs or betas, those are hidden states, right? The protocol does not see them. The protocol just sees them, the realized demand, Y, and the price. And so this needs to be estimated to set optimal price. It's like basically an estimation problem, which like it's obfuscated in the current setup because there is just like this naive estimator in the protocol. And then the other thing to note is that these parameters change over time, right? It's a dynamic economy on top of the market. So like demand for resources changes at the block level, like block by block, basically. So this is what makes the problem inherently dynamic. And actually, this is the first work that acknowledges this important like dimension. Like there were previous works in potentially doing multi-resource pricing, but they all assume like some static demand process, right? So instead, like we model like this evolution of demand as a mean reverting process, and then we use some filtering techniques to optimally estimate the hidden states, basically. So
can I just interrupt for one? So the economist in me comes in here. I just wanted to understand exactly what the mechanisms are that are going on. So we're talking at the moment at the mandatory, essentially a mandatory payment that you have to make to the validators, correct? I mean, just like in the EIP, what 15, I forgot what number it was, right? Protocol, right? Where the fee has two components, and we're talking about the mandatory part. We're not talking about the other part. Is that fee also going to be a two-part solution as a 1559? Thank you.
So here, like what we are doing today is all base pricing, right? Like so this is all about the base fee, and in 4844, like in blob transaction, you also have tips. So maybe like one thing I should say, like I didn't give a broad like literature review, but one thing I want to say is that there is actually like a lot of interesting work, potentially even by some people in the audience, around like resource pricing, like from a game theoretic perspective, right? Is that because here we're setting the base fee, but then there is this additional component which like is basically a bid. So like people have worked on like what are the incentive properties for like miners, the people that collect those bids, and like the kind of mechanism design properties of this. When you look at the base fee, these questions don't show up, right? Because it's basically like this optimal estimation and control problem where like the protocol needs to set kind of this base number that then can be like bidded upon, let's say. Okay, yeah, so then once you have a way to do optimal estimation, basically what's the goal, right? So the goal is like to find a pricing policy that minimizes the long run average expected cost of the system, right? And then essentially like we define this expected cost really looking at like from first principle, like how the congestion mechanism was designed and what the protocol needs. And basically there is two components. So like if you look in the objective function, basically at each block, we have like two norms, like two notion of like deviation. One is like how much the realized resource demand, Y, deviates from the target, T. And the other one is what is the block-to-block price volatility, basically, right? And like The first reason is important because you want to do congestion management is like the #1 reason why we implement this mechanism. The second part is needed basically for user experience. Like you don't want the fee to go up like 2 orders of magnitude from one block to another. And like if you're sending your transaction, this could cause like problems where like transactions fail or like user end up paying like much more than they were expecting, basically.
So the economist in me comes through again. And so as an economist, we like to think of, you want to maximize welfare, right? So you seem to attribute welfare to fees, but you could also attribute welfare to utility. So that would be use, right? So the number of transactions that would be captured in a blob, a very efficiency of that could be included in that. So is that included here?
Yeah. So this is more of an engineering approach, right? In the sense that sorry if I trigger anyone.
I mean, if you are a social operating system, then you should care about welfare, not.
Yeah, we do care about welfare. So like what I'm saying is that in this work, like we didn't look at welfare directly, or although like you can back out welfare from like basically the structure of the problem we set up, right? Like you can look at user surplus and but we don't go into details. There is other works that like characterize welfare. For example, there is this stream of work by Andreas and collaborators. The problem with those is that they're very interesting from like an economic. I'm also an economist by training, so like there is like some interesting like economic properties, but the policies that you characterize, they don't tell you much. Like they're a bit far from like being able to like maybe you have an algorithm that can be implemented in Ethereum, right? So like this is kind of like the principle I was saying, that we want to try a setup where like we can check robustness, we can check that it's simple so that it can be implemented and has some good properties. Yeah, so that would be my answer. But yeah, definitely welfare is important. I don't want to dismiss that. Yeah. Okay, yeah. So maybe like just quickly on like the optimal policies that come out from this problem. So essentially, we have like a relatively simple update rule. So here, essentially, the optimal policy tells you that like you should set the price for block K+1 as a combination of like the price that you observe at block K and this parameter which we call aim. Okay. So this is like the weighted average for the future market expected clearing prices, right? So essentially, like you take the latest price that you observe, you via optimal estimation, you form an estimator for like the future clearing prices, and you take the average of that. So this is similar to like some work by Garleano and Pedersen that some people may be familiar here, that they consider different problem in quantitative training, but like with the similar setup. And then the idea here is that essentially what this rule does is it handles a trade-off between like responding to local market changes, but also like being robust to local noise, right? Like the current price may go up for like just random noise instead of like the fact that parameters are now shifting. And then just continuing, like another point I want to make is that this rule sets prices for all resources jointly, right? So, and in particular, like there may be some cross effects between resources, and these are taken into account in the optimal pricing, which is not the case for like the way we do things today in practice. Like we price 1559 transactions and 4844 transactions in parallel, basically. And then I won't go too deep into this, but there is actually like for people that are interested in like resource design and like questions like similar to what Andreas was asking before, there is actually this concept. We define this concept of eigen resources. So essentially, like you can decompose like once you have the demand structure, you can actually decompose into a set of independent problems, right? So and then if like you design resources in this way so that like you have bundles of independent resources, then you can price directly the bundles and you don't need these like maybe more complicated joint update rules, like each bundle is priced separately. And like we show like some results and some way how to do this. So this maybe I'll go a bit quicker because I already talked about. Yeah, but this is a depiction of like on top is what is happening today with 1559 and 4844, like kind of parallel updates versus the joint update that our rule does. Okay,
is there any concern or even the possibility that if you take the other side, right? So the rollups that want to post the data blobs, that there is strategic behavior in response to the particular setup that you have. I'm not sure if I can explain this properly, but you kind of want to optimize maybe the size of a blob then, right? Because it becomes a problem. And there, I mean, so there could be a concern of you know, is it optimal to optimize to take up the full space, or is it would you want to have a smaller blob, so less data that you post on there? Is that somehow something that, you know, validators like because less resources?
Yeah. This is a fantastic question, and is actually the subject of the next session. Right. Yeah. So great segue. So here, essentially, like in this work, we focus on like strategic behavior from the rollup perspective, right? Which have to post this data on the layer one. Yeah, this is a joint work with Ed Felten and Akaki at Off-Chain Labs. Like this is the team that built and still manages most of the Arbitrum chain. Yeah, so maybe like to give like a more pictorial description of like what Andreas was referring to. So then now we have like this entity, which is a rollup. And here, maybe I just call it a batch poster, which is one of the modules of the rollup sequencer, right? So then essentially what you have is like there is this stream of transactions that arrived over time. And let's assume at rate R per second. And then this batch poster needs to decide when to post and like how much data to post, right? And basically there is two avenues. Like one is use the blob, right? And the other one is like just use the cold data as you were doing before, right? And essentially, like if you use the cold data, then you pay like a price G, which is like the gas price, times the some P0, which is like demand for compute, plus P1 times N, which is like the data demand for the aggregate of transactions in the blob. But you pay all in gas, right? Because this is pre-4844, there is no other market. And then on the other side, if you use blobs, essentially you'll pay like some compute cost in gas, right? Which I was referring before, like 0 times G, plus the blob price, right? B. So these are like the L1 cost that you incur when you need to post transactions on the layer one. There is also this additional parameter A, which is a waiting cost. So essentially, like basically, you think about rollups as these like basically they are blockchain systems that anchor to the layer one, but like the key property of blockchains is security, right? Trust minimized security. So for rollups to be secure, they need to post data to L1, right? because that's how they verify their computation, right? Otherwise, like it's just a server on Amazon Web Services, right? So here we introduce this parameter A, because essentially like waiting too much degrades the experience of the rollup user. They don't get the full security until the data is posted. And yeah, again, like as I said before, like there is also the blob size is like limited, right? But we kind of abstract away from this. So essentially here we are trying to like set like a steady state model, like the system that I described before, right? It's a bit different setup than the previous work. We don't look at dynamics here. We look at steady state of this system, and we try to determine what is the optimal posting strategy for a rollup, right? So essentially determining the optimal time to post blobs, which also determines like how big or how filled these blobs will be, right? So essentially, we write the aggregate cost of posting a batch as a function of the time that you wait. And then essentially like we look at the waiting time, like the delay time that minimizes this cost. And this gives us like a measure of cold data cost as a function of like the key parameter that I was introducing, P0, P1, A, and R, and the prices, like gas price and in this case gas price, because we're just looking at posting cold data. But in the case of blobs, we can do the same thing, depends on both gas price and blob price. So they kind of like if we look at the two markets separately, like the posting strategy is kind of similar if you try to do maybe like some comparative statics on the rollup size, right? Like so essentially like rollups that are bigger, that have a higher rate of transaction incoming, they post larger blobs, they post more frequently, and then of course have lower posting costs per transactions because they can pack the blobs more efficiently. Like I'm not talking about this here, but we also have like we also model like compression efficiency in the paper. It's not like super important here, but that's also like something we model. So basically now there is the question that Andreas was asking, okay, what do you do, right? So here there is no outside options, right? Like these rollups need to post, like they don't have the option of like not posting data because otherwise their system break. But they can decide like which market to use, and there's going to be an equilibrium, right? So essentially like we can write these simple inequalities that characterize like when it's better to use blobs, right? And so like if the blob price is smaller than like some constant which depends on like the rollup size, importantly, then you always want to use blobs. And this is what's happening today because the market is still oversupplied, basically. The other thing is that of course we can rewrite this to essentially like highlight the effect of like having a larger rollup, right? So essentially like the larger a rollup is, the more likely it is to be posting blobs, and then also like the less sensitive a rollup is to delay. Obviously also like into like this is not counterintuitive, is intuitive, like it's also more likely to be posting blobs.
I'm just going to point out here again so that, I mean, there's a lot in this number R potentially, right? Because I think there is actually work to be done. So for all the PhD students again, right? And actually endogenizing that portion a little more, right? So there's the fee that the rollup charges, which kind of is important, and then there is possibly utility obtained in the rollup, right? All of that is kind of in reduced form involved there, right?
Yeah, exactly. It needs to be unpacked, right? Like this is kind of like the first work in this direction. Yeah, as you said, like R probably depends. It's endogenous, right? Depends on like the price that these people pay, and the composition of like the price that you charge at L2, then what its effect on the L1. Yeah.
And so also so Fahad actually wrote this to me, and I'm gonna I'm not gonna read this out in detail, but I think basically what he says is you create, if some rollups contain most of the applications, right? So then you can create a strategic oligopoly where that determines the prices and the way how you maintain market power and so on by using these effectively.
This is interesting. So the oligopoly would be this is like rollups that control like a specific type of applications, or like yeah, what
can I just interject?
Yeah, please.
Yeah, so the point I'm making is that if everybody is deploying their dApps on Arbitrum and no other rollup, or even just a couple of them and no other rollup, then the thing is, yeah, I could use a different rollup, but the point is there's no dApps that are actually deployed there. So it's like moving to a city where nobody lives.
Yeah.
But then the point is there's effectively market power that and Arbitrum could decide that, well, why should we pass along the gains from the lower cost we have? Why don't we strategically raise prices on people? It's not like they're going to start using rollups that have no dApp activity on them.
Yeah, exactly. So like totally right. As in cities, there is like huge network effects in these rollup systems. The switching costs are also quite high. So there is frictions, right? Like people cannot like frictionlessly move between systems, even if there were, right? Even if there were rollups that have exactly the same app functionality as Arbitrum, like, there will still be friction. The reality is that like each ecosystem is different. So yeah, this is true. So here again, you are thinking about, so the way to think about the cost that the rollup user incurs is like there is two components. One is the cost, which is basically the base. Let me not call it base cost, so that we don't confuse with L1 base price. So one is the cost that you need to pay to the sequencer, because the sequencer needs to cover the cost of posting on L1. And then the second component is the congestion on L2, or like whatever pricing. It couldn't, in the future, maybe you are suggesting that is not just congestion pricing, it could be like profit maximizing prices.
Right. So I guess one way to frame my question is, what stops the sequencer from having discretion on that second part and just deciding to behave like as an oligopolist pricer, as opposed to more mechanically trying to pay for his costs?
So like there is nothing stopping them, because it's a permissionless system. But I guess this is the part where like maybe two things. One is there is frictions, but it's like still order of magnitudes less friction than like Web 2. Like when you're using AWS and you have contracts with like AWS, like switching all your system to like another cloud is like for some people it's costly. For some people it's nearly impossible if they have built like their entire thing on there. So yeah, one is like the cost structure is different. There is frictions, but I think like it's basically much lower than current state. The second thing is maybe governance, like the fact that is like the users of these systems are the people that control via token governance the fees as well, right? So like there is some alignment between like the users and the owners, like who sets the fees. So like in the future, today, like some of these sequencers are still centralized, so there is an entity running them. But in the future, when they are community owned, then maybe that's another check for avoiding extractive pricing.
Well, you could imagine that a firm builds a lot on a roll-up, right? Builds a lot of functionality on a roll-up and then becomes, uses Ethereum just basically to settle every now and then, but basically because of network effects, just corners the market, right?
Yeah. And
that's really interesting features. That's actually really interesting stuff. I mean, it goes beyond what you have there, but I think there's a lot happening there.
Yeah. And I think there will for sure be those cases, right? So essentially, like rollups will be different in like size, right? But also like functionality. Some will be like more specialized, and some will be like more generic, right? Just like Ethereum today. I think like for the specialized ones, like some will be like firms, right? So I totally believe that some of them will try to like maximize profit from fees, but then like the larger ones, like if you aspire to be an economy, right? It's almost that you can be a firm or you can be an economy. Then if you aspire to be an economy, like basically you want like the welfare maximizing taxes, right? Like you want low taxes, basically.
Anyway, so I have a question here from the Q&A, and I'm just going to call on Abdullah maybe to ask the question directly.
Sounds good.
Do I have to do anything? Allowed to talk. There you go. You're allowed to talk. Work? No? There you go. Abdullah, you don't want to ask a question in live? Want me to ask a question? Okay, not asking. So then I'm going to ask the question. So he asked the question is the new blob transaction redundant? It could be implemented by call data.
Yeah, I wouldn't call it redundant in the sense that you can use the call data as you were doing before, but there is an important property that like these blobs have like some cryptographic gadget, the way they are committed into the L1 that allows to do data availability sampling, which essentially expands the capacity of Ethereum to host data in a trust minimized way. So that's kind of the important thing here. It's like this is like a resource which much higher capacity that technological improvement was not possible before. Yeah.
Okay.
Maybe let me check the time. So we are supposed to finish at in 15 minutes or?
Yes.
Okay.
But if ideally you leave like 5 minutes or so for some questions from the audience.
Okay. Yeah. So then maybe let me switch gears a little bit. So then something else we explore, which is quite interesting now, since like we've seen that like the equilibrium result depend a lot on like the roll-up size, right? So no one stops roll-ups for like teaming up and posting blobs together. Like you need a little bit of technology to make sure that like the data packed in a blob is like essentially is identifiable which data comes from which rollups, but like it's totally doable. And so like we kind of model this problem where like what happens when like rollups team up, right? So now you have a rollup of like a capacity which is the sum of the capacities of all the rollups in the coalition, let's say, or in the group. Let me not say coalition because so probably triggering, like in the group. And then like the benefits is that like due to like compression and lower delay, you will have like lower overall cost. But then the other problem is that since like some of the rollups, like the smaller rollups, most likely were using cold data. Now, like you have this effect that you are actually like changing the demand for blobs, like potentially increasing it and potentially increase the blob price. So like essentially then we look at what happens, right? So, and the price can go down if like rollups were already, most of them in the group were using blobs because of efficiency, but it can also go up if there is like some new demand for blobs that comes on from people that were using cold data before. So here, essentially, we have a small example. Maybe, yeah, I can go through this a bit quickly. So essentially here we have an example where we have a rollup with like, let's say lower traffic, like rate R. And then we have higher traffic rollup with like rate 4R. And then what if these two rollups join together in a group? Then they have a rate of 5R per second, right? And then essentially, you can see that like using our characterization, we can compute the cost, and like the aggregate cost per transaction is like 2 over square root of 5 C, which was the cost of the smaller rollup. So like essentially like here, both rollups save on transactions, but the question is like then how much they save, right? Like then the value that these rollups get for joining is basically dependent on like how much they split the savings, right? And so like here we are not maybe experts in fair allocation and things like that. So maybe like there is some interesting ideas that come to mind to people in the audience, but we try like some we try to characterize like some simple approaches, right? So one is like you split pro rata per transaction. So like every transaction will pay the same for posting after joining together, right? So then the high traffic rollup pays 4/5 of the posting cost, and the low traffic pays only 1/5 because of like the lower load. Another way of potentially sharing the savings is like equal percentage savings. So every rollup should get the same percentage savings compared to posting alone. And here, essentially, like this is like much more balanced. So now, like the high traffic rollup saves much more, right? Saves pays for 53% of the blob, and the low traffic pays for 47%. And then the third approach, like we actually set up like some an axiomatic Nash bargaining scheme, and we try to characterize like what's the equilibrium of that. And essentially there is like the split is again once again more in favor of the low traffic rollup, which pays 30% of the blob cost, while the high traffic pays 70%. So essentially, like these are just like 3 cases we consider. I think these are kind of as the question before from Fahad around like charging L2 fees. This like cost sharing scheme is also like an economic decision of the rollup entity that is or the third party that is hosting this blob sharing service. And there is people already like looking into building this because it is clear that there is benefits, especially for the smaller rollups, right? That otherwise they probably would need to use cold data, or they wouldn't have the efficiency to like pack the blobs in time. Yeah, so maybe this is like for people working in this area, this is also like an interesting area of research. Okay, cool. Yeah, so for the last part, I'm going to like look at this market has been live for about a month and a half. So I'll look at what we're seeing in the live market for blobs, and then briefly discuss some future improvements. So we were live on March 13th, and like since then, so in these two charts, you can see that there is this green square, which is like the date when 4844 went live. And on the left, you can see the aggregate cost paid by rollup, like significantly went down. And then on the right, you can see the activity in terms of like transaction per second from like all rollups on Ethereum. And then you can see that it went really up, like by 50%, from like 100 TPS to like 150 TPS. And part of this is because like directly like the fees literally went down 10x or like even more on some of these rollups, right? So people started deploying applications, which some of them are maybe futile games, but they were not possible before, and the people like to play them. So then we have this 50% increase. So this is great, right? It's a great feedback, and like makes us comfortable that like as we like keep increasing the capacity, really like the capacity of the Ethereum system as a whole will go up, and eventually will kind of like overcome and really like leave in the dust all those like monolithic chains that they just try to like do all the processing. Yeah. And then a little bit deeper into what's happening in the market right now. So yeah, on the left, there is those parameters we were discussing before, right? So like I'm showing over time, there is a green horizontal line at 3 blobs. This is the number of blobs per block. And then there is a red horizontal line at 6, right? And basically, I'm showing like in this diagram, both like there is some vertical bars for the realized number of blobs at each block. You can see them. Sometimes they go above 3. I mean, probably you cannot see them clearly, but like basically the point is that like at each block we may have even 6 blobs, but if you take a 2 hours moving average, we are constantly like below the target, right? We are maybe hovering around 2 blobs per block, and that is why the base price is still 0. Like I'm putting this 0 way. But like yeah, people are using the market, is like clearly live, but having this 0 price may cause like some unintended consequences. So here actually you have the base fee over time, and then there was a week at the end of March where essentially like since prices were 0, people were like, oh great, we can post whatever data to Ethereum. So like there was a project called Inscriptions, which is basically like using the cold data to post like some images, some NFTs, like similar to like for the people that follow like in general other protocols, is similar to like inscriptions on Bitcoin that exploit like some unintended functionality of Bitcoin to just shove data into the system. So here, since the price was 0, these people were doing the same. But what happened is quite interesting, right? So essentially, like the dynamic pricing of like 4844 like increases prices exponentially, right? So if the blob capacity is full, if the blocks have like 6 blobs in them, then the fee starts going up at 12.5% every block, every 12 seconds, right? So like immediately the fees jumped from like $0 to like $50, $60 per blob. And so at that point, like these random use cases were not any more viable. So they still tried to do it. They saw that maybe like if they slow down, like the price goes down, but like I think at some point they realized that like is not viable. the rollups were still posting because I think their willingness to pay is very, very high, right? Like it ultimately, like, yeah, maybe if you have feedback, the rate of L2 transaction will go a bit down, but people are using this system in their everyday life. So it's like Argentina. Yeah, there is like 100% inflation, but like some people still use pesos, right? So
can I just ask one thing? I thought this blob data is also not permanent, right? Isn't it?
Yeah.
So if you do it on Bitcoin, right? So it's there forever, but here it's not, right? Why would you? I mean, you know, in NFT data, posting NFT data seems, you know, then the NFT would be gone if the data gets deleted. No?
Yeah. So yeah, I don't have a good answer to that. I ask myself the same question. Like, I don't know the details of what kind of data these people were posting, right? If it's just like data about like the transactions that were happening, or if it's like the whole thing. Yeah, so I don't know how their system work. Maybe they just need the data to be available, or like in which case, yeah, this was a legitimate use. Otherwise, it was simply spam. Yeah.
I just wanted to have an eye for time. We have just 3 minutes left.
Yeah, we are almost done. So then this bears the question of like, what's the future price of these blobs, right? It's an important resource in the Ethereum economy. So some people from like Polymarket, which is a prediction market also on Ethereum, try to run basically a prediction market, future type market for like block price. And yeah, basically they divided like the price into buckets, and they asked what will be the gas price per blob 1 month after 4844 is deployed. And the way the market is resolved is like 1 month, you look at the median price over the blocks of a week prior. And then you take that median price as like the oracle price that resolves the market. And of course, the price was almost zero. So because we are not at capacity, so it seems easy to predict the price. But I feel that when we reach like a level of like these blobs are really in demand, it may be challenging to predict the price. And like big price swings are like very problematic for rollups. So there is interesting questions there. Yeah. So in conclusion, basically like future improvements are related to a few things I discussed, but let me summarize them. So one is there is some work from like Ethereum R&D to increase capacity, which is called like data availability sampling is one of the main upgrades that will come in the next few months. Then there is also like some way of doing like data availability out of the Ethereum protocol, but secured by the Ethereum asset. And this is one example is EigenDAA from EigenLayer, which is like actually it's the same design of Ethereum DAS, just with different parameters, like different nodes, and then just using Ethereum security. And then the second area is like there is very active R&D and a lot of development here into like packing more data into blobs. One is like proof aggregation systems for like basically zero knowledge rollups coming together and like proving together like valid state, and then better compression. And then the last one I want to mention is related to the last thing I discussed, right? Like ideally, like these rollup users, they want like stable prices. And so like, is there like new mechanism like selling bulk blob space in advance, or maybe even futures for blobs? Yeah. So with this, I conclude, and thanks for the attention. I'm open for
Well,
questions.
thanks so much, Davide. That was fascinating, and I hope actually the audience also got lots of ideas for, especially the economists, for research topics and questions that require answering. I have two questions which I want you to have like a 30-second answer to. They're kind of related. So the first is by Bofu Zhang, and the second is by Michel Fabi. So Bofu asked basically, do you see rollups as a temporary solution and that there still will be some form of sharding? And the second, and because it's sort of related, but is from Michelle, she asked basically, is there a difference between optimistic and ZK rollups in terms of optimal resource pricing? So if you could just give a very quick answer to both of these.
Yeah. Okay, so the first answer is a resounding yes. Like rollup are here to stay. Like some rollups have like assets in the tens of billions on them. So like they are big economies. I mean, they are still small compared to the potential that they have, but like they are big systems. The second answer is also definitely yes, because ZK rollup has like this additional resource, which is the prover. It's like in the design of a ZK rollup, there is not just the sequencer, there is this additional entity, which is the prover, which has resources to like be able to compute the proof. So there is definitely like big differences in like resource pricing, also like let's say from like a market structure perspective, how do you organize and decentralize a market for provers? So there is just some early work on this that maybe I can share some links if there is some channel after the talk. But definitely like interesting area. I also like sometimes post on this, so like maybe you can follow me on social media like to get the updates.
Yeah, this is probably a good way to actually find the information, and then you can contact you. You can slip into your DMs. All right, okay. I think we're at the end of time. Davide, thank you so much again for your presentation. I just want to very briefly plug our conference, which takes place on May 23rd at NYU. We have 6 research paper sessions, a keynote with Maureen O'Hara. We have a fireside chat with where Cam Harvey is interviewing the CFTC commissioner, and the Ethereum Foundation, thank you again, will be explaining the economics of Ethereum in more detail during the session. So with that, thanks you so much, everybody, for attending, and I'll see you hopefully soon in 2 weeks. Thanks, Davide.